Great then. So I'll welcome everybody to the next session in this track, where we'll hear about upcoming or the currently released Sockeye 2. And this presentation has been pre-recorded by Tobias Doman.
Okay, shall I proceed?
Yeah, I think we can get started.
Hi, I'm Tobias Doman. I'm a machine learning scientist working on Amazon Translate, and today I will be presenting Sockeye version 2. Sockeye is our neural machine translation toolkit. The work for this presentation at AMTA was done jointly with Michael Dendekowski, David Vela, Xing Niu, Felix Hieber, and Kenneth Heafield. So before I go into the details of what's new with Sockeye 2, I first wanted to introduce Sockeye to those of you who are maybe not familiar with Sockeye yet. So Sockeye is our production-ready sequence-to-sequence framework that also powers Amazon Translate. So in general, while we focus on machine translation, we have it as a general-purpose framework that can be used for any kind of sequence-to-sequence modeling. As we use it ourselves, we designed it to be a flexible experimentation platform for researchers. So the intention is that it can be used both for training models, but also for extending it, doing model variations and performing machine translation or sequence-to-sequence research. It's based on the MXNet deep learning library, which gives you fast training and inference speed, multi-GPU support, and also the support to both GPUs and CPUs. It's open source software developed with the Apache license, and we do the development publicly on GitHub. So you can go and check out Sockeye on GitHub. Other than being a sequence-to-sequence framework, just wanted to list a couple of features. There's TensorBoard logging, where you can monitor your training performance while you train your model. And a couple more features such as checkpoint averaging to average the parameters of multiple checkpoints, basically giving you slightly better performance for free. Lexical shortlisting for improved inference speed and best translations if you're not only interested in the best translation. Sockeye itself is very easy to use, so it's a Python package. So what you can do is you can basically go ahead and you can install it through pip. So just pip install Sockeye. Once that is done, you can then run the training command, given that you have some plain text training data. So while there's more advanced features where you can binarize your training data, all you actually need to get started is you feed the training data into Sockeye with a source and target parameter, which gives you a model folder. Once the model is trained, you can just pipe from text on the CLI into the Sockeye translate command. You can give it a model and it spits you out the translation. So we try to have the command line interface be very simple and easy to start, while still offering advanced features through CLI arguments. So with this, after the small Sockeye introduction, one of the biggest things that changed actually under the hood, which is relevant for anyone who wants to extend Sockeye and make model changes, is that we moved to MXNet's new deep learning API called Gluon. Gluon basically allows you to, on the one hand, still have static computation graphs, which allow very fast training and inference. But at the same time, if you turn off these graphs, basically turning off what MXNet calls hybridization, you can still set breakpoints and very easily debug your code. Overall, using Gluon, we were able to simplify our code quite a bit because we no longer need to set up the computation graphs. It's just these computation graphs are created behind the scenes under the hood. On the right-hand side, we see a small example where we create this very small, basically one-layer neural network. We define basically the parameters, and then inside the forward method, we define the computation. And all that is now needed in order to create our computation graph is called this net.hybridize. And this is it. And if we comment out the hybridize, we can set breakpoints and we can inspect basically intermediate outputs, which makes development much easier. Overall, the Sockeye 2 has about 25% fewer lines to this simplification, and is about 40% faster even. In the development, we focused on mainly the now state-of-the-art in machine translation, which are transformer models, as they're usually both higher in quality and at the same time also faster due to the high amount of parallelization. The default settings for the transformers in Sockeye are the pre-norm setting, which essentially means that each transformer block, the layer norm is not on the residual connection, but rather on the input to each function, leaving the residual connection alone, which allows for training very deep models without training instabilities and other issues that one can sometimes see with transformer models. In practice, what we found to work very well is training very deep encoders and shallow decoders. The reason is that on the encoder side, you can fully parallelize across all positions, while on the decoder side, due to the auto-regressive nature of these models, you cannot parallelize at all. Therefore, despite having very deep encoders, if you look at the overall latency, it's actually much lower if you have a shallow decoder. If you look at the model quality in terms of the BLEU score, you don't, usually you get very similar BLEU scores, so the model quality is not affected. Another improvement to the Sockeye 2 is that we improved the source factors. So source factors are essentially additional input token sequences that are parallel to the normal input sequence. So you could, for example, have part of speech tags or something else. Or for example, a case factor where you lowercase the input and then have at every position encode the case through a factor. Previously, you could concatenate the embeddings of the case and the normal embedding. Now we have support for concatenation, summing, and averaging. And we also added support for weight sharing of the word, basically the source vocabulary and the fact vocabulary. On the right-hand side, you can see a small experiment where we have a baseline that's trained on case data and then several variants that are trained with source factors, either where the input data is first normalized and then we represent the case through factors, or the last two rows where we the input of the model is basically the cased and the uncased word, where it can make sense to share. We then evaluate on the original test set and then lowercase, capitalized, and uppercase versions. And we can see if you use source factors in this application, it can make the model a bit more robust against these modified versions of the test set. A very important aspect of Sockeye 2 is the training speed. So I'm going to be talking about three different aspects here, namely the automatic mixed positions, where some of the layers can be run with 16-bit floating point numbers, distributed training through the Horvath library, and large batch sizes to amortize some of these costs, as we'll see. These are all available out of the box, part of Sockeye 2. As soon as you have Sockeye 2, there's no other further step necessary to use that. Okay, so what is automatic mixed precision? In the newer NVIDIA GPUs, starting with the Volta architecture, NVIDIA added tensor cores. Tensor cores basically allow for very fast floating point 16 or mixed FP16, FP32 computations. For example, you could have the input to be FP16, but the accumulation to happen in 32 bits. Of course, when you go to FP16, with a reduced precision, it's sometimes tricky to get training to still work. So the big question is, can we get this to work in practice? So one particular way to both get some speedups and at the same time to still have basically the safety that we're used to with the FP32 training is this automatic mixed precision that MXNet also supports. Basically, what this means is that given our computation graph, MXNet knows which operations are safe to convert to FP16 and which operations are on a block list that we really rather want to have the full precision for example, the exponential function here or the softmax. In the model itself is kept in FP32 and only some operations inside the computation graph are downcast for the speedup. Overall, what we need to still make sure is that we don't have any overflows, so MXNet will check the gradients before each update to make sure that we didn't have any overflows. and protect against this. For distributed training now, so that is done with Horowod. Horowod is a library that allows this basically distributed training in either a setup where you have a single or multiple hosts with each single or multiple GPUs. Each in that setup you have multiple trainers. So for example, you could have one trainer per device or one trainer per GPU. Each trainer, so it would be the Sockeye process, basically is independent of the other one, so you don't have a parameter server that's centralized, but you still need to make sure that you synchronize these gradients across the different hosts. And for gradient synchronization, that is really very much dependent on the hardware, how efficient this can be. In a setup like this in the picture on the right-hand side, you see that some of the GPUs are connected to NVLink, which is an interface developed by NVIDIA that allows very fast communication between GPUs. So it's very fast to exchange gradients, whereas where other GPUs are connected through PCI, which is much lower bandwidth. Using Horowod and the NCCL library from NVIDIA, we can make sure that we basically get the we make use of this topology that not all GPUs are connected equally. And in order to exchange gradients, all reduce is used instead of broadcasting all gradients to all other GPUs. Yeah, and therefore, what it means in practice is that we can make use of the best basic bandwidth between all these GPUs that are connected in a heterogeneous way. Okay, so now we have distributed training, we have automatic mixed position. So we know that synchronizing, despite being relatively fast with NCCL, is still expensive. And for AMP, we need to check our gradients. So in order to still get benefits and try to avoid synchronizing our data too often, one trick one can do is accumulate gradients, which basically leads to effectively very large batch sizes. Large batch sizes allow you to have a very high throughput in terms of the number of sentences per second. Now, if you go ahead and train a model with very large batch sizes, while you get a very high throughput, of course, it doesn't mean anything because the number of updates per second is actually lower because the computation required for a large batch is higher than for a smaller batch. So a trick that people use in practice is that with a larger batch sizes, you have better gradients. Better gradients allow for larger learning weights. So one rule of thumb is basically that you can scale the learning weight by the square root of n, where n is the batch size. So basically, when we have large batch sizes, we can increase the learning weight accordingly. Speaking of learning weights, so the default learning weight scheduler that we use in Sockeye 2, or in Sockeye in general, is the plateau reduce learning weight schedule, which basically allows for a data-driven way of adjusting the learning weight. What happens in practice is that we take the validation performance, which we monitor during training, and whenever we plateau in the validation performance, we reduce the learning weight by a factor. This in practice allows you to do not have to specify a schedule beforehand, but just adapt to the training. And with that, we find that often you find a better point faster in practice. In this experiment, we compare the inverse square root learning weight decay, and we see that we reach a higher blue score in slightly, or almost the same blue score, but in slightly less time. So training speedup is one of the aspects of Sockeye 2. The other aspect is inference speedup, and there we have support now for quantization. So first of all, yeah, what does that mean from the hardware side? So Intel, for newer CPU architectures, has specialized 8-bit and mixed 8 and 32-bit operations, and also some operations now specifically designed for neural networks. Intuitively, what this means, if we have 8-bit operations, we can potentially run more operations in the same CPU cycles if we have the right kind of instructions provided by the CPU. And now in Sockeye 2, we make use of that through the int.gem library, which basically implements 8-bit integer arithmetic to do operations like the fully connected layers. And in terms of training it, nothing changes. So you continue to train a 32-bit model. or potentially a mixed precision model with 32 bits and some parts of the graph downcast to 16 bits. And then at runtime, we can basically convert the model, or you could even store it in disk in the 8-bit format, which would give you a slightly smaller model, or actually a much larger, smaller model. Yeah, and then you can tune these, or Sockeye will basically create these scaling factors so that you have a minimal loss. And what this means in practice is what we see here in this benchmark. So what we trained here is two models. One is the 20 encoder layer and 2 decoder layer transformer, and the other one is a 6 encoder layer, 6 decoder layer transformer. And we compared once in the baseline performance and then quantized. What we see is if you look at the blue score is basically only slightly worse when we go to the quantized model. But if we look at the same number of CPUs, we see that the throughput in terms of tokens per second is much higher when we do use int8 instead of FP32. Okay, and now to summarize. So Sockeye is our production-ready sequence-to-sequence framework that can be used for machine translation and other sequence-to-sequence tasks. I hope I was able to show that the command line interface that we have is pretty easy to use, but that doesn't mean that we don't have advanced features available, so these are also available as they become necessary. Now moving to the Sockeye 2 version, we focus on the one hand on transformer models. Of course, we might also incorporate other architectures. For example, recently we integrated simple recurrent units on the decoder side to also have fast inference for transformers, for decoders. We switched to MXNet's Gluon API, which makes implementing models much easier. And at the same time, we still have the same speed we're used to. It's even slightly faster, but we can debug our code now with breakpoints instead of having to find some workarounds for static computation graphs. Source factors are improved, so there's a couple more options that were not available before. We have very fast training through Horovod, either on a single node or on multiple nodes, and CPU inference is sped up through 8-bit quantization. Sockeye 2 is an open source library. It's available both on GitHub and can be installed as a Python package. And we also include Docker files that make it a bit easier to get set up in terms of CPU or GPU optimized builds. This is it. I'd be more than happy to answer any questions in the live Q&A.
Okay, thanks for a nice talk, Toby. Oh, and Huda is here she's going to run the Q&A session for this talk. Looks like we have Toby online, so.
Yeah, right.
Hello.
So we have our first question from the chat, which asks if GPU inference is also faster in Sockeye 2?
Yeah, so we actually had a recent contribution from NVIDIA to Sockeye that actually made GPU inference also faster. So there's, if you look at the GitHub version of Sockeye, so this is not something we had in the initial version of Sockeye 2, but very recently we merged the change. So yes, the answer is yes.
And we have a question from Kevin Du, which thank you for your talk, and asked if you can mention briefly what are the plans for Sockeye 2 in the next year or so, specifically what new features are planned to be implemented.
Yeah, so we don't have any public roadmap that we follow and then implement and follow through. So I think it's just in general, we add kind of new architectures as they become available. We use Sockeye for our own research. So as we implement things and publish papers, we would also include those in the Sockeye version and publish that. And then, of course, it also depends on what kind of pull requests people do and what others contribute back to Sockeye. So one thing we did with Sockeye 2 is also kind of simplify a lot of the code. So we removed some features. Maybe there's interest from the community to bring some of them back. So that also is a kind of dependent on the community.
So Matt Post asked, is the cross-host scaling provided by Herovid basically for free, or does it require extra configuration? And have you tried to push this at all? For example, trying to obtain massive or multilingual models?
Yeah, so it's provided out of the box in theory through the Horowitz library. If you want to do this multi-host setup, I guess there's you need to configure. So each Sockeye process is essentially running as a normal training process that doesn't really know that it's multi-host, but then through Horowitz you can still get the multi-host configuration, so to say. Same as if you run on a single host, and now with Horowitz we would recommend you run one process per device. So it's essentially a multi-process training setup. To the individual Sockeye process, they don't know anything about that, but overall, if you use, for example, MPI for running the setup, and then you would need to specify basically the multi-host setup with MPI. And then Horowitz would take care of synchronizing gradients and doing things, and Sockeye wouldn't need to know about this. Yeah. So I would say it's there out of the box. There's a little bit of configuration, of course, so you still need to do it with Horowitz.
I don't see another question yet from the chat, so I'll ask one of my own. Oh, here just one came. Steve Richardson asks, sorry, I may have a delay on my end. How widely is Sockeye being used by academics or in enterprise? And can you share at least a few of your users or some approximate number of downloads?
Yeah, okay, so I don't have any numbers that I can share because I don't have them. So I think one thing that we have on the GitHub page that's being maintained is the list of publications that make use of Sockeye. I guess one indication, what you could also do is you could look at the Sockeye papers, the 1 and 2 paper, and look at citations, which should give you a pretty good impression of how many academics use Sockeye. And yeah, I don't have any concrete numbers to share, unfortunately, though.
We have a follow-up question about how easy it is to install and use Herovid. Specifically, is it just a simple pip install, or is it something beyond that?
Yeah, so I mean, for Sockeye, it's this normal pip install. You need to install Horowitz itself as well alongside. So so I think once you have set that up from the Sockeye perspective, it's pretty easy to install. And for Horowitz, it's just following the usual standard instructions for installing Horowitz. So it's not terribly difficult, but yeah. And Horowitz is also available as a Python package.
Following up on Steve's question, so Sockeye is primarily developed by Amazon. Can you talk a bit about the trade-offs you have between the research and production aspects you have there?
Yeah, so I mean, basically, if you kind of think about who's the prototypical user of Sockeye, it's basically us. So it's researchers that have an interest of running something in production. So we have basically kind of both interests. So on the one hand, we want to have Sockeye be kind of maintainable. We have a lot of unit tests. We try to document our code. But at the same time, we also, if you want to run an experiment, you can just make a potentially maybe even hacky solution, run an experiment and do something, right? It doesn't stop you. As long as once we want to merge it back to the GitHub branch, of course, we want to make sure that the code is kind of then at that point documented and tested and properly integrated. So I think there isn't, that much of a kind of conflict between the two. As long, we do try to maintain a single code base for everything. So we do have the same kind of code for experimentation and for production. So I think the only requirement, so to say, is to once we go back from research to production, at that point we need to clean up code and make it well tested and documented.
That makes sense. So we have a, I think, related question from Steve, which asks, if you're able to say if there's any kind of enhancements Amazon uses or integrates that are not necessarily available to the public in Sockeye.
Yeah, so I mean, we try to make basically the GitHub version of Sockeye yeah, like the major version of Sockeye and not have it to be like a, I don't know, only a kind of project where some of the changes make it out on GitHub and we maintain many more features internally. Of course, if you, I don't know, run, say, some research experiments or something else, we keep code internally, we run experiments internally. I think the goal is to have everything public at some point. But yeah, that is not to say that we wouldn't keep maybe some of the features if there's a reason not to share them. But I think our intention is to develop publicly and to share any kind of features as long as we can publicly as well. And so to have the main version of Sockeye to be the GitHub version. And I think it's pretty feature complete in terms of what we offer. So.
Great. I think we may need to wrap up to give people time to hop to the next session. But I will applaud on behalf of everyone since we cannot all. And thank you for your talk and for all your answers.
Thank you.
Thanks. Okay, we'll see everybody in the next session.